Okay, hi, I'm Doug Ocherek. I am the manager of the Lustre Core Development Group at Intel's High Performance Data Division. It's quite a mouthful. I came to my first Open Fabrics conference a year ago. At that time, I was working for a company called WhamCloud. At WhamCloud, we were supporting the Lustre file system, and we got acquired by Intel about July of last year. So Lustre is a open source, scalable parallel file system. As open source, it runs fine on all sorts of commodity hardware as well as custom-built chassis that do storage. It was designed and is aimed at the HPC community, which is its predominant user. I say predominant, and later I'll explain why I say that. The Lustre community works under the umbrella of the OpenSFS group, which SFS stands for Scalable File Systems, and Lustre is the predominant file system that they're overseeing right now. They take the membership dues and use that to put out work that they would like to see, the community would like to see have done for RFP, and then fund the various projects that get done to Lustre. So in my talk, I'm just going to give a brief update of the work that's been done recently to Lustre and the kind of problems and issues that we're working towards solving with Lustre. And I'll be sliding into another project that we're working on called Fast Forward, which is a DOE-funded initiative to move towards exascale storage for the exascale computer that they want to see by the year 2020. And so that'll be feeding into a lot of the other things that you've heard from people talking about scalability. Okay, just briefly for those who may not be too familiar with Lustre, I'll do a quick overview just to get the terminology right, as you will need that for the rest of the talk. Over here we have the Lustre clients, and so in HPC those are your compute nodes. Along the top we have two servers. One is called the management server, or the MGS. The other is the metadata server, or the MDS. The management server maintains the file system's configuration. So all nodes, when they start up, go here to get what the configuration is and how the whole file system comes together. The metadata server maintains the metadata for all the files stored in the cluster. Commonly, the MGS's job is not too heavy, so these two servers tend to be merged together in a lot of places, and they just run under one server. Down the side here, we have the OSSs, which are object storage servers. The data, and behind them are the OSTs, and those are the actual disk arrays that they're going to be using to store the data. So the ideal with Lustre is your metadata stored on the metadata server, and your file data is striped across the OSTs, via the OSSs. And this is where we get our scalability, is as you add more OSTs and OSSs, you get a larger and larger file system growing into the size of petabytes where we are today. And it also gives performance because we're striping across the OSTs, and so when we're reading, we can do parallel reads and parallel writes to get the performance levels up to very high levels. We also support what are called Lustre routers, and this is where we run the Lustre stack on a machine with multiple NIC cards, and it goes into forwarding mode. And so as LNet packets, I guess I should just step back a moment. One of the layers of Lustre that does the networking is called LNet, Lustre networking. That's the only one I'm going to talk about. I won't go into any other software layers today. But LNet packets, as they come into a router, it's able to see what network they're destined for and forward them automatically. And this gives us the ability to forward between different fabrics, such as InfiniBand to Ethernet and Ethernet to InfiniBand, or some proprietary fabric. LNet is designed to be pluggable, so you write these little plugins below it to support different fabrics. And today we support Ethernet, InfiniBand, and there's some proprietary ones such as Cray's Gemini and Aries plugins. So very briefly, that is the overview of how Lustre works. Development is done on a train model, so every 6 months we come out with a new release. And so if your particular feature is ready for it and it's been well tested, it'll go out with the release. And if it's not, it'll be held back until a future release. So I'm going to go through now some of the ongoing projects that we're working on today to address different issues with Lustre, and then on to some future ones that we're hoping to do. So the first thing is having only one MDS is a bit of a bottleneck if your application requires a high rate of file creation, file destruction. So OpenSFS funded 3 projects to address this. The first one is called SMP Affinity and LNet. right up until version 2.3 of the software, which came out 6 months ago, LNet had one global lock for resources, and LNet runs as a kernel module, and so being a lock, we end up in the spin lock mechanism and churning the CPUs whenever we got too high a rate of operations to the MDS. The SMP Affinity splits the cores up, if you have more than 8 cores in your system, splits them up into what we call CPU partitions. And each CPU partition maintains its own resource list and its own locks. And peer connections are anchored to a CPU partition. So we're basically getting finer grain locking, and we're distributing the load a little more evenly over the CPUs and preventing collisions as much as possible. Above LNet is an RPC layer called Portal RPC, and we did improvements to the locking and threading in parallel with the SMP Affinity feature to help reduce collisions at that layer as well. But the third feature is the one that I think is going to help potentially help the most. The distributed namespace feature, or DNE, is going to allow us to have multiple metadata servers. And so with phase 1 of this, the Lustre administrator can designate which metadata server will work for different directories. So you can assign a directory tree or subtree to a specific metadata server, and then all metadata operations will go to that particular server. And so a smartly set up network should have a nice distribution of metadata operations across multiple servers. Future versions of DNE will have a more automated process of migrating and moving data between the metadata servers to improve performance. I indicated earlier that right now Lustre is focused on HPC, but we would also like to see it adopted a bit more in, say, the big data, cloud, and enterprise worlds. And one of the initiatives that we started is Hadoop optimizations. I was going to skip past this pretty fast, but with all the talk about Hadoop, I thought I might just say a couple more things about what that means. So the theory is if you're running Hadoop on the Lustre file system, all your nodes see the same file system, so transferring files between the nodes is no longer necessary. An optimization is to actually just transmit file paths between the nodes, since they all see the file system. So presumably, if you have very large files and you assume that Lustre is doing its job and is very high performance, you should get a fairly good optimization of your Hadoop's cluster when it's trying to gather all of its map data together. That's ongoing. I don't have any numbers or charts to show you, but we're hoping to see some pretty good speed-ups of Hadoop with that particular feature. The next one, consistency. As being a file system, you have to have consistency or nobody's going to obviously use you. And just like having FSCK in Linux to do file system repairs and file system integrity checking, we in Lustre have LFSCK, which is a parallelized way of going through the nodes and looking for orphaned nodes and basically cleaning up your files. And this is an ongoing project to keep this up to date, because as new features like DNE come into play, we have to be able to do consistency checks across multiple MDSs and so forth and so on. So this is a sort of a never-ending project of ensuring that every time we add stuff to Lustre, we always have a way to keep the file system consistent going forward. Performance, Intel and Xyratex worked on a network request scheduler. This runs in the clients, and effectively it works at the RPC level to reorder your RPCs based on a profile to optimize the use of the servers. So thinking of what the servers are going to have to do, reordering the RPCs can improve how well those back-end servers are performing for us. Xyratex also added in a 4 megabyte bulk RPC, which allows us to do larger file operations. And along with Lawrence Livermore Labs and Intel, we created sort of a pluggable architecture for the back-end file systems the servers are using. And this allows us to move beyond ext4, which is all we've supported up until now. And one of the first file systems we're going to be adding in for the back end is ZFS support. And maybe down the road, something else like Btrfs might come into our radar. The next feature is a pretty exciting one. HSM, or Hierarchy Storage Management, was done by CA in France with a little help of Intel. And it brings into play the ability to migrate data from our system into other storage, such as tape, and to be able to pull it back again. So it gives us the ability to move between layers of storage. And this sets the foundation of an architecture which can be used for other features, which I'm going to be mentioning in a moment or two, and sets a very good groundwork. So in terms of upcoming projects, what we would like to do for Lustre going forward, one is to improve its small file I/O. Today, Lustre is fantastic if you've got large files and you're streaming to those, those arrays of OSSs. But if you've got a small 4K file, it's not very efficient because you have to do an RPC to the metadata server, then you have to do RPCs to the OSSs just to get that small file. So we will be doing a data on MDS project whereby if the file falls below a certain watermark, which is settable by the administrator, we will store the file data alongside of the metadata. So when you go to get the metadata, you actually get the file at the same time, and then you don't have to talk to the OSSs at all. And if the file goes above that watermark, we then migrate it from the MDS out to the OSSs again. So it gives us sort of a happy medium between small file I/O improvements and then the scalability of having all our OSSs. The next one, OSS striping. Today we stripe across the OSSs for performance, but we've had customers say that the back-end storage, if we want to have active standby failover, we need to have dual-ported storage, which is very expensive and not something we'd be able to do in the cloud. So many have asked us to have a feature where we can replicate the OSTs so that if an OSS or an OST goes down, we can just use the replicated version. And so we're going to start working on that project hopefully soon. Continuing with cloud and enterprise enhancements, today the clients can support dynamic addressing, but no other nodes in Lustre can. So we can't support DHCP in the cloud today, which is a huge blocker. So we'll need to come up with a way to map targets to addresses, or what we call NIDs in LNet, in a more dynamic and better way than we're doing today. LNet, as I indicated, is a kernel module, and all of its configuration is done via module parameters. And so if you need to change any of those, you have to unload the module, which takes down your file system, and then load them again. We've had a lot of calls to start doing dynamic configuration so you can do things on the fly without taking down your file system. And so that project is also lined up. And the last one, it's not really configuration, but the last one is channel bonding, or what I've heard called here link aggregation. And all of our InfiniBand customers seem to be asking for this. They want horsepower. They want more and more and more than what we're getting today with InfiniBand. And we were hoping that at some point we would get this from the drivers itself, such as OFED. And so if anybody knows of a way to do this or has something that won't be 2 or 3 years out, but maybe a month or two out, please talk to me. I'll hug you, because this is a big feature we really, really want. And the alternative, if we can't do it in the driver, is we'll have to do it in our LNet layer, generically, where we balance our messages, LNet messages out over multiple connections. We'd rather not do this, but this is such a highly asked for feature, we have to do something, and soon. So just my wish of this group. If you can give me the InfiniBand link aggregation soon, I will be so happy. For performance, storage tiers. So having a tier of SSDs and then having a tier of rotational drives below it, and then use the HSM feature to intelligently move information between the tiers based on usage profiles is something we would like to do going forward. And scalable monitoring. Today, all the nodes ping their peers to find out if their peers are alive or dead. So if a server goes down, every node has to find out on its own through pings. This is a very inefficient and not a great system given the size of these clusters and as they keep growing. So we need to get some sort of a health network where when a node goes down, the information about that is quickly spread to all the other nodes so that we can adapt quickly to that. So that in a very quick nutshell is what's been going on in Lustre, sorry, and where Lustre is going as we move forward. With regards to exascale, this chart kind of gives a bit of an overview of where we are today with Lustre's performance. That's the 2012 column, and where we need to be predictably in 2020 if we want to be considered part of the exascale machine that DOE wants to see happen. I won't go through the numbers, but you can see that they go up by quite a big scale, like object creates going from 100,000 creates per second to 100 million per second is quite a jump. Peak I/O bandwidth today, we can get up to 1 to 2 terabytes per second. We're going to be expecting 100 to 200 terabytes per second. That's peak, of course. Sustained I/O bandwidth, today we can look at between 10 and 200 gigabytes per second, but for exascale we're predicting we're going to need to be able to do 20 terabytes per second. So this is a challenge. This is a huge challenge, and I think you've seen many speakers mention that already. So to get us moving in that direction, the DOE put together an RFP to get companies to start working on solutions to move us towards that 2020 goal of an exascale machine. Part of that RFP were three components: processor, memory, and storage. WAM Cloud bid on the storage component and won the contract. And along with WAM Cloud, we have the HDF group who's going to be doing HDF5 modifications, EMC to work on the burst buffer manager and an I/O dispatcher, and Cray to do scalability testing. When WAM Cloud got acquired by Intel, we had to do a renegotiation of the contract and add more work in from Intel's side. So Intel is going to be contributing an arbitrary connected graph computation engine, and DDN is going to be adding in versioning OSDs, or object storage systems. So we will get some versioning in the future with exascale. So the requirements of exascale and this fast forward project is we're going to be expecting constant failures at exascale. And I think Mark said this in his keynote, is that this is just inevitable. As we go faster, we're going to see a higher rate of failures and errors. As a file system, though, we have to guarantee data consistency and data integrity from end to end. And at the same time, we have to stay always available. We just can't stop and run LFSCK to repair it and then start up again. That's not possible. So we have to deal with these errors on a running system without stopping. So the thinking is that we'll be following a transaction model for writes and reads, so that if something goes wrong, we can roll back and not stop all the different operations going on. A pictorial view of what we see as the exascale I/O architecture is we'll have an exascale machine, and we'll still have a shared storage system like we have today with Lustre. In between the two of them, we'll have our site storage network. Well, those brackets are interesting. Not sure where those came from. Anyways, the exascale machine will be a huge array of compute nodes, all of them sitting on top of an exascale fabric of some sort, which will have to have incredibly high bandwidth and low latency. At the end there is a series of I/O nodes that all of the compute nodes will send their transactions to when they want to talk to the file system. Those nodes will need a burst buffer, presumably NVRAM, to deal with the bursts and then to lay them out to the site storage network in a nice even pace. The site storage network, relative to the exascale fabric, will be expected to be much lower bandwidth and much higher latency. But because of the burst buffers, we'll be able to use it in a more predictable fashion. And then on the shared storage side, we'll have the typical storage servers like we have today with Lustre. And presumably, we may need the metadata to be cached in NVRAM to speed up file creates and destroy operations. Yep. All right, so the project goals of Fast Forward is to, well, effectively make the storage the tool of the scientist. And so by that, we will move compute to the data, or data to the compute as appropriate. I'll explain that in a moment. And to do all of this with high degree of fault tolerance. So the diagram, which is an eye chart, hard to read, but in the diagram we have a scientist who fires off a simulation to the exascale machine. Exascale machine churns out vast amounts of numbers that flow into our storage network. At the end of it, the scientist is notified. Now at this point, rather than having the scientist's computer go out there and do analysis and have it to keep dragging data to and from the storage network, we are going to try to move the compute to the storage network by letting the scientists write little jobs that run in a sandbox on the storage servers. So, for example, if we support Python, he can create little Python fragments that can do MapReduce or do some sort of analysis, ship those over to the storage network, and then having good locality to the data, the storage network can be to do his analysis at a very high speed and shoot the results back to him. So the I/O stack for all of this has to have, well, three big features. One is non-blocking. It has to be a completely asynchronous model. Synchronous will be the death of exascale. It's not possible. Two, it needs to be transactional so that we can stay consistent even in the face of a failure. And low latency, which we say probably means OS bypass and go straight from user space right out to the hardware. the I/O stack in terms of its layers. At the application layer, we are expecting to have multiple APIs. Traditional APIs for those applications that still need a POSIX view of the file system, and newer APIs designed to capitalize on the speed of this whole exascale architecture. We'll need in between an I/O dispatcher that can deal with the differences between what the applications need and want and the way that things are stored, and also to manage the burst buffers and the cache mechanisms that sit between the application and the storage network. And lastly, everything is going to be surrounded around something called DAOS, and that stands for Distributed Application Object Storage. And DAOS is an object container, if you will, that is scalable and shardable across OSSs and is going to become the sort of the unit of storage for this whole architecture. If you wish to know more about that, this is a whole massive topic unto itself. I'd recommend going to our wiki page, which is at wiki.hpdd.intel.com, just to read up more on what DAOS is. So pulling together the stack and the earlier picture of the architecture, we'll have our compute nodes with the applications, and they will talk to one of multiple APIs such as HDF5, MPIO, or POSIX. There will be an I/O forwarding client that will forward these transactions to one of the I/O nodes where there will be an I/O forwarding server. Those two will talk to each other over the HPC fabric using MPI or portals. The I/O nodes will have an I/O dispatcher who is going to be managing the transactions to NVRAM's burst buffer and moving things to a modified Lustre client. That Lustre client, which today supports POSIX, will have extra support added in to be able to work with these DAOS containers. And then the Lustre client, as it does today, will talk to the back-end servers over the SAN fabric, which we're still seeing is using InfiniBand and OFED. So one final thing is, now that we're going to have this huge scale out of servers, we need to come up with a way to distribute information between the nodes, such as fault tolerance and peer discovery. So the current thinking is to use the gossip protocol, which is, in a very simplistic terms, where one node tells two nodes and that node tells two nodes and so forth and so on. And in a certain number of hops, we distribute information out over a very vast number of nodes. We want to use that to share fault tolerance information, to do peer discovery, and just to have general health network style communication. And so these servers will get collected together into collections, and we'll use a tree overlay and then use the gossip protocol within that tree overlay to quickly distribute information. And that's basically that. And that's the end of the presentation. Very quick. Ooh, good. Very quick. So if anyone has any questions. Oh, I think I see one over here.
Hi, you mentioned about some efforts to see how Hadoop works in the Lustre environment.
Yes.
And you also mentioned about taking compute to the data.
Yes.
So I was just wondering if you're exploring moving the clients, moving the compute of the Hadoop to the OSS.
In terms of Hadoop, I don't know, because of just the sheer number of Hadoop nodes will be a little overwhelming. Okay. That particular feature is aimed at the Fast Forward project as we move forward. Although, one thing I should mention is a lot of that Fast Forward stuff I talked about will be rolled back over time into Lustre. It's not a clear cut that we go from one to the other. And if we get enough demand for it, there's a possibility we could go down that path. But again, we need a lot of server nodes to make sure that they're not too overloaded, because they still have to be server nodes as well for the file system, as well as running, the Hadoop code. So we have to be careful about how we do that.
Right.
The idea was little tiny Python scripts just to do some quick analysis and not bog them down too much.
Okay. The related question is, from an architecture point of view, how do you see Lustre offering better capability than HDFS for Hadoop?
Well, it's kind of in the sense that that Lustre is designed for large amounts of data, like obviously moving towards even exabytes, in a stable platform that is viewed equally by all the nodes instead of being adapted specifically for Hadoop, for example. My understanding, and I'm not that familiar with HDFS, but it seems to assume local storage, is my understanding with HDFS. And that's one of the things that we're trying to address by simply giving everybody the same view of the same storage to reduce the amount of file transfers that goes on.
And also the lack of RDMA with HDFS. Right?
And then there's that too, although I get the feeling that that's going to be addressed at some point by somebody in this room, for example. But we were just trying to use the file system almost as a communication mechanism, because we already support RDMA. That's how Allnet works today with InfiniBand. And so we already have all that in place. And so if we can give you your files across all your nodes more efficiently, then perhaps that's an easier way to go. The changes and optimizations we're doing is at the Java object level. And so changes will occur even with HDFS in our world to help promote the use of Lustre and efficiencies there.
All right, thanks.
With the questions you have about the channel bonding, if it doesn't actually fall into your lap, how much effort do you think it would be? I mean, a year out, 2 years out?
Well, I mean, okay, if you talk to a developer, it's only maybe 6 months out, but then there's testing, right? So I would say more like a year. We have prototypes of things that others have done, and they'd like to push up into the community tree, but we're looking at them from the perspective of what is the right solution architecturally going forward. And many have said that the right architecture would be if InfiniBand does it for us, but in lieu of that, we have other backup solutions.
Yeah, we saw some of it last week.
At LUG, yes. Okay, yes.